Most people are intrigued by the heliotropic nature of sunflower, but what is not always clear is the survival mechanism behind heliotropism. For the sunflower, these survival mechanisms are heat differentiation, fluid dynamics, and pushing pressure. This chain of events begins at the pulvinus, the area where the flower meets the stem. When sunflower is exposed to sunlight, part of the petals shade a portion of the pulvinus, causing heat differentiation between the shaded and sun-exposed side. This condition causes growth hormones, which are light shy, to move to the shaded side, causing influx of potassium ions, which creates concentration gradient. Concentration gradient triggers osmosis, or fluid movement, from sun-exposed side with low concentration to shaded side with high concentration to maintain equilibrium. This fluid movement causes turgor pressure, resulting in expansion and elongation of the pulvinus. An elongated, expanded flexible side exerts pressure on the sun-exposed rigid side, producing a pushing pressure towards the sun.
These survival mechanisms of heat differentiation, fluid dynamics, and pressure also become the building blocks of our working hypothesis. Change in temperature equals change in pressure equals fluid dynamics equals surface articulation. Our visits to various manufacturing plants brought exposure in the manufacturing process in the area of casting, laminating, tempering, and phase change. We experimented and tested several materials in an effort to discover the materials that are best suited for modeling our basic principles. Hydrodynamics is a branch of science that focuses on the motion of incompressible fluids such as water, rooted in the physical conservation laws of mass, momentum, and energy. This discovery shows the principles of hydrodynamics by pumping water through containers of varying sizes and shapes. We continue to conduct material research studying various material properties such as conductivity, emissivity, reflectivity, and translucency. As we made the connections between our basic principles and the materiality, the idea of our unit emerged, a shading device. A container filled with gas is heated, causing the gas to expand, producing a push outward to provide shade. However, we were not equipped for the precision required for such a system. Fluid leakage, low pressure, friction, and other difficulties left our models lacking. Our heart said yes, but our test said no. It was time to reevaluate.
We revisited our material study. We experimented with our basic principles. We wanted to make a more universal and inclusive connection with our principles and our unit. We were looking for a unit that transcends linear connectivity to a multidimensional connectivity, a unit that encompasses our working hypothesis. After testing, experimenting, and modeling, our new unit emerged, a fluid dynamic thermal controller. To determine the best shapes for our outer and inner chamber walls, we conducted the fog test. For the outer chamber, it was determined that the S-shaped wall worked best for directional airflow control. For the inner chamber wall, it was determined that the rounded shape worked best for cooling because it allows for minimal obstruction for airflow. The hook shape worked better for heating because it captures and directs heat into the building. A thorough study of the microclimates helped us to understand the thermal connectivity and airflow between the building and the local environment. We determined that there are hot spots in the west and southeast, and therefore ideal locations for our unit for maximal heat collection. We also discovered that predominant winds were from the southwest and northwest, so we oriented the unit vent to take advantage of this. The result is a unit that provides continuity between outdoors and indoors, providing a rich indoor-outdoor experience for the occupants. Our thermal controller is a supplemental heating and cooling system generated by solar heat that functions by taking advantage of heat and pressure differences to drive airflow. During the cooling season, the sun radiates heat into the thermal controller. As heat builds, it rises up and out of the unit's vent, pulling air from the ground tunnel to replace it. This provides cooling. During the heating season, the unit vent and ground tunnel are capped, and the system becomes a closed loop. As heat and pressure build up within the controller, the heat is pushed into the floor pipes, releasing heat. As the air moves to the other side, it loses heat, causing it to cool and drop down, and the cycle begins anew. From earlier material research, we determined that in order to maximize solar radiant heat gain, the thermal controller would be made of a highly transmissive clear material. Only the north side of the unit is covered with black painted insulation for maximal absorption and minimal obstruction. For the piping, a low emissivity and highly conductive material absorbs and transfers the treated air to the occupied space. This piping is insulated from below to retain the desired temperatures.
In 10 years, the simplicity of the system ensures longevity, and we foresee the system being adapted for use on neighboring buildings on campus. Just like the sunflower, when the thermal controller receives heat from the sun, it produces a pressure gradient. This pressure gradient triggers fluid movement in an effort to create equilibrium. So we conclude that just as the sunflower uses these survival mechanisms of heat differentiation, fluid dynamics, and pressure to adapt to the environment, our building does the same.